Tyler, you think we're good to go?
They come up with sort of
All right,
fake
then.
data to see how the systems respond.
All right. Good afternoon, everyone. I see a lot of familiar faces from previous events for this exhibit series. I'm excited, very excited to introduce our next guest speaker in the program following on the shoulders of giants, How to Find Killer Asteroids. And we have Tyler Linder with us today, who has come in to speak about his work with NASA and this, if I can be honest, rather terrifying prospect from a layperson's point of view. I hope you haven't found any that are, well, I guess you'll get to that. But it's, we all might be running for cover at the end of this, who knows. But it's a great pleasure to have you here speaking with us. I can't tell you how much we appreciate this, and thank you all for coming and attending these program series. We're so excited to offer them. It's amazing the talent we have in our own backyard and with connections here at EIU. So without further ado, Tyler, would you like to take over? And
sure.
As part of our appreciation,
thank you
we
very
gave you a
much.
certificate for participating with us in our exhibit.
Thank you very much.
Thank you.
So thank you to Booth Library and EIU for putting this on. Like many things I say yes to, you get an email months before, say, hey, will you give this talk? And you're like, yeah, sure, what the? And then you forget about it for 6 weeks, and then you realize, oh, that's coming up, you know. So I'm going to give a talk today that I've given before, but modified for what I hope is the more knowledgeable audience of actually some, giving a little bit more details. So before I start, I've given a couple hundred professional presentations to amateur astronomers, to schools, I mean, you name it. And my wife reminded me earlier this week, you better invite your mom. So my mom and dad are here. So I don't think you guys have ever heard me talk before, so I'm really excited. I walk around a lot. If you need me to stop walking around, tell me, okay? Oh, come on. All right, maybe I won't be walking around as much. All right, so this is a panoramic view from Cerro Tololo, which is acronym CTIO. It stands for Cerro Tololo Inter-American Observatory. It is in the Andes Mountains, about 100 miles west of La Serena, Chile. This is a 4-meter telescope. The easy conversion from meters to inches is 40 inches is 1 meter. So that's about a 160-inch diameter primary mirror. It's huge. It's over a foot thick. This is my baby. This is a 1-meter telescope, and that is NASA's largest full-time Southern Hemisphere asteroid telescope. So I have this telescope, and there's some down on the other side of the mountain, which I've got more pictures on. But our operation is extremely cheap, also known as budget-friendly, because the cheaper you are, the more likelihood NASA will give you money. So we have not paid the $250,000 to repaint the dome, because that's actually more than the entire yearly budget we have to operate that telescope. So if you would like to donate to telescope dome painting. All right, so here's the legal page. This is really boring. Bear with me. I am a NASA independent contractor. I do not speak on behalf of NASA. NASA has provided no input into this presentation. All conclusions implied or spoken are that of my own and not represent any opinions of NASA. The views and conclusions presented in this presentation are those of the authors and do not represent an official opinion expressed or implied of NASA. Please do not go on Twitter and say, NASA astronomer Tyler Linder said this. I will get hate mail immediately, okay? I am an independent contractor. How this works is majority of NASA research, they put out yearly solicitations. It is open to the general public, including public, private universities, and major corporations to apply for grants to do the research NASA is asking for. This means they don't have to pay health care, they don't have to pay benefits, and at any time they can cancel you, and they're out no money, okay? So don't go on Twitter because they'll cancel you. So the overview of the presentation is a little bit different than probably some of the other presentations in this program. First thing is I like to talk about myself. Then we'll talk about the size of the solar system. And this is the key part that majority of people don't understand. The size of the solar system to a killer asteroid. Then we'll talk about why we care about asteroids, why you should continue to tell your Congress and representative that it's important to fund my research, and what and where are asteroids, the overview of NASA's mission to protect Earth, and lastly, how we actually do it. I cannot ever protect Earth. I can just tell you when to kiss it goodbye. Who am I? I'm 33, had a birthday yesterday.
Happy birthday.
Thank you. I am married to my beautiful wife Danielle, who's a speech-language pathologist. She got her BS and MS from CDS here at EIU. We met at EIU. We have a 3-year-old son, Owen, who, if I look tired, it's his fault. In 2004, I graduated high school from Marshall, Illinois. I went into the Navy for 4.5 years and was on the aircraft carrier John C. Stennis in the engineering department. That's truly where my love for physics came from, because I had a job where I had to fix everything. So I got to work both with the reactors, with the steam, with the catapults, with the aircraft. I loved it. So when I got out, Illinois had a program that if I come back to a state school, they'll give me 4 years free tuition. So I did that at EIU and got a BS in physics in 12. I was hired basically by a NASA grant prior to graduation, and I started before I graduated, to expand NASA's asteroid monitoring network to the Southern Hemisphere. And I'm the only Southern Hemisphere asset NASA has. I realized very quickly I needed a PhD. So in 2015, I started my master's, completed that in 2017, and since then I've been still working on my PhD. I hopefully am 12 to 18 months, but I've been saying that for about 6 months, so we'll see. I fell in love with astronomy due to Jim Conwell, professor at EIU, who's now retired, and Bob Holmes. My first telescope operation was the EIU Observatory, and I started doing asteroid observations, and the very first night I ever submitted them to NASA, they rejected them and said, these are horrible, get yourself corrected. So since then, I'm actually the number 2. I've submitted the second most by a single person near-Earth asteroid observations ever. Number 1 is Bob Holmes, who I work with. So between the two, we have produced almost 25% of all near-Earth asteroid measurements for the last, I think, 8 years? Okay, so now I need to thank National Geographic, because they do much better presentations than I do. So we are going to talk about the size of the solar system here. If you've never got to see this video, I love it. It truly puts in perspective what we're going to talk about next. And let me know if you can hear it in the back, or if it gets too loud.
If you look up an image of the Earth and Moon, you're going to get a picture where they're quite close together. Something like that. But in reality, the Earth and Moon are about that far apart. That is the Earth and the Moon to scale. Taking the same concept, but for the solar system, every single picture of the solar system that we ever encounter is not to scale. If you put the orbits to scale on a piece of paper, the planets become microscopic and you won't be able to see them. There is literally not an image that adequately shows you what it actually looks like from out there. The only way to see a scale model of the solar system is to build one. Welcome to Black Rock Desert. This is Alex. I'm Wiley. He's going to be behind the camera. I'm going to be probably making a lot of mistakes on camera. We have 36 hours to measure the distances, trace out the orbits, and set up a time-lapse shot from up on top of a nearby mountain. To create a scale model with an Earth only as big as this marble, you need 7 miles of empty space. So that's why we're here.
Why did you guys come?
I don't have a job. At this scale, the sun is 1.5 meters, so about that big around. So we are driving right now to Mercury, and we've arrived. Venus is the same size as Earth. I have a world in my pocket somewhere. And Earth. And this is Mars. Got a couple of robots rolling around on that one. Once the time-lapse is ready, we'll drive each orbit with a light. Hopefully you'll be able to tell just how big they really are. Onward to the outer planets. Jupiter. That tiny light out there is our sun, just over a mile away. The sun's way, way out there now. This is it. This is the edge of the solar system.
So right now, it's about 7 a.m. We just woke up right before the sun's about to rise.
We are on Earth's orbit. Wiley's over there holding our sun. Cue the dramatic sunrise music.
So if we've made our model correctly, your perspective from where Earth is on the model will match your perspective from standing on real Earth. So if you look back at the sun, you will see that the model sun and the real sun are the exact same size. And that's how you can tell that the proportions are correct. There are 24 people in the entire history of the human species, billions of people, who have actually seen the full circle of the Earth with their own eyes.
Following the breakfast, the astronauts went to the suit room where they donned their spacesuits.
This is man's attempt to get to the moon.
0. We have liftoff. Liftoff at 7:51.
In Earth orbit, the horizon is just slightly curved. When you head on out to the moon, that horizon slowly curves around and upon itself, and all of a sudden you're looking at something that is very strange, but it is very, very familiar.
Oh my God, look at that picture over there. Wow, is that pretty?
You can put your thumb up, and you can hide the Earth behind your thumb. Everything that you've ever known, all behind your thumb.
Not any bigger than that, way up there.
It's really beautiful. You can cry.
That's what I really wanted to try and capture. We are on a marble floating in the middle of nothing. When you sort of come face to face with that, it's staggering.
So thank you, National Geographic. presentation before, maybe you do a little bit more now. But why do we actually care about asteroids? I love the analogy in that presentation that uses Earth as a marble, because asteroids are much, much smaller than Earth, and yet can still kill us in this vast space that we call our solar system. So we care about asteroids because A, they can kill us, B, it's untouched material that has not had anything done with it other than solar radiation since the beginning of the solar system. So if you want to know what the planets were made out of, you look at the asteroids. An asteroid impact is the only preventable natural disaster. We can't stop a hurricane yet, we can't stop a tornado, but if we can find the asteroids and know about it ahead of time, there's a hope, or a chance, we can move it. So here's some of the sizes that we end up working with in the world of asteroids. So of course the sun's diameter is 1.4 million kilometers. Earth is about 13,000 kilometers, and the moon is around 3,500 kilometers. We call one astronomical unit, by definition, the distance between Earth and the sun. This is about 150 million kilometers, 93 million miles. The distance between the Earth and the moon is only about a little under 400,000 kilometers, and this is a very critical number that we call one lunar distance. The reason is because when we're watching for killer asteroids, we're just not okay if they hit Earth. What if it does a close flyby and takes the GPS satellites out? What if it hits the moon, cracks the moon? What is the moon effect for human race? What happens if the tides stop? What kind of ecosystems in the ocean stop? So the chain reaction of something relatively small impacting both the Earth or the moon has very drastic impact to mankind. And so this is where, when you talk about damage assessments, what is the second, third, and fourth generation of damage? The same concept is actually when, in bomb analysis, okay? Let's say you have a bomb go off, but if the bomb is next to a power plant or some big propane tank, then you can get secondary explosion. It's the same concept where you get a chain reaction, and something very small can now have a much wider effect. So in asteroids, we only care about things that orbit inside of Jupiter's orbit. And if you don't know, in AU, remember 1 AU is the distance from Earth to the Sun. So Mercury is 0.4, Venus 0.7, Earth is 1, Mars is 1.5, and Jupiter is out to about 5.2. An asteroid, by definition, is something that orbits within 6 AU, so basically Jupiter's orbited inside. Comets are much, much farther out. They're outside Neptune. The only reason we see a comet is you've had that comet somehow have an orbit change from a collision, and then we send it into, and its new orbit now comes closer to the sun. Comets are frozen, they're ice, and what we actually see as a comet trail is actually the sun heating up the surface and sending out water vapor. That's the oversimplified version. If there was a comet scientist in here, they would slap me. Asteroids don't emit any type of this debris. We don't see asteroid tails until a year ago. Now we've started to recognize that some asteroids can have outbursts, but that research is very, very in the infancy. So I say this because one of the asteroids that we have a spacecraft orbiting right now, Bennu, they just came out last week and said we are starting to see outbursts on the asteroid. But that's all brand new research, and so comets, icy, you heat the ice, it melts off, gives you a tail. Asteroids, solid rock. Okay, so there's a pretty clear difference in the research area. A near-Earth asteroid, well, we'll talk about that here in a second. So what is an asteroid? It's a rock. At the beginning of the solar system, there was a failed planet between Mars and Jupiter. And if you look at the distances here, you shouldn't be too surprised. We have all of the inner solar system planets all kind of crammed together. And then all of a sudden we get a huge jump out to Jupiter. But then the outer solar system planets, which is Jupiter beyond, we have these vast distances between. Basically, Jupiter got too big too quickly at the early stages and have prevented another planet from forming outside of Mars, right around 2.2 AU. We now call that the main asteroid belt. where there are millions of asteroids orbiting the solar system. And these objects are just rocks. I mean, you can call them dried rocks, dead rocks. You know, for 4.5 billion years, they've just been saturated with radiation with no atmospheric protection, okay? So it's just rocks. We see craters because smaller rocks have slammed into them and ejected some material, so the overall population is decreasing in size, but they're just rocks, you know, and 99% of the time, they're no hazard to us. To give a comparison here, and one of my favorite plots, I actually found this earlier this week, this is actually to scale. This is not the largest asteroid. This is actually asteroid number 21. It's only about 132 kilometers wide. These two right here are actually near-Earth asteroids, and the human race has spacecraft orbiting them. Ryu is actually Hayabusa 2. This is the Japanese second asteroid sample return mission. And OSIRIS-REx, which is a University of Arizona, NASA, NSF, Lockheed Martin partnership to do the US's first asteroid return mission. This is 1 kilometer. Bennu is about 0.5 kilometer. 1 kilometer is a global killer asteroid. So if you ask yourself, if this object breaks up, how many 1 kilometer asteroids can you get out of this? The answer is a lot, okay? So the population of the near-Earth asteroids are very small compared to the main belt asteroids. The main belt asteroid is a semi-stable system, but Jupiter is a big bully. So remember, Bennu is 1/4 the size of Ryu, but it's been kind of scaled. But these are the two, these are actually taken, this is taken from OSIRIS-REx, this is Hayabusa's 2 close-up image. They both look like spheres, all right, kind of like, drawing a blank, but oblate spheroids, okay? You get a little bit fatter right here at the equator. And we do think that's due to some rotational effects that Don and I are doing some research to investigate, but when you look at their surface, it's just cratered. It's rocks. They're all just sitting there. The problem is if this is on a collision course, it would kill us. So where are asteroids? By definition, the near-Earth asteroid population is any asteroid in which any part of its orbit comes within 1.3 AU. This is called perihelion. The closest point to the sun of the orbit is less than 1.3 AU. Remember, Earth is at 1, Mars is at 1.5. So NASA has kind of set this limit where if you get close to halfway between Mars and Jupiter, or Mars and Earth, we start really caring about you. If you're outside that limit, we don't care about you anymore. Mainly because we have to find a way to reduce the number of asteroids we do care about. Main belt asteroids are between Mars and Jupiter, and comets, of course, are outside Neptune. Now, there's a lot of confusion when it comes to meteors and meteorites and all this other really dumb naming convention that's, inherited. A meteor is something going through our atmosphere. This could be space junk, space trash, rocket booster, or majority of the time, an asteroid. If it hits the Earth, it's called meteorites. So majority of the high-end, if you're a chemist, your high-end research is going to be done on the meteorite population. And NSF sends people to Antarctica, because meteorites are dark, Antarctica is white because of all the snow and ice, that you can find these to study them. One of the reasons for OSIRIS-REx is that you're getting basically an un-Earth altered sample of an asteroid, because we haven't been able to study it any other way. Here's an overview, kind of like a top-down picture of the solar system. This is Jupiter. Remember that the Earth to Jupiter is 5 times the distance from Earth to the Sun. Everything white here is a main belt asteroid. It's not, Mars is at 1.5, and kind of the center, everything orbits right around 2.2 AU. It's actually from about 2 to 3.2 AU. Jupiter is still a major bully here. It will interact with these asteroids and have them nudge each other. Sometimes a piece will break off, sometimes you have major cracks. These collisions are what then put asteroids in an orbit that then could be called near-Earth asteroid. At the beginning of the solar system, there were no near-Earth asteroids. It's literally Jupiter and Saturn being a big bully with their gravitational tugs, basically manipulating the main belt asteroids to then put them into a near-Earth asteroid orbit. If you would like to know about the Lagrange points here, L4 and L5, there's actually trapped asteroids. NASA just funded a spacecraft mission to go to 15 of them. They funded it 2 years ago. They're starting to build the spacecraft now. It will fly in 2022 and go to 15 Trojan asteroids. So if you hear the term Trojan asteroid, we are referring to the L4, L5 captured asteroids of Jupiter. We believe a portion of these population is actually captured from other solar systems. Because the second largest gravitational force in the solar system is Jupiter. So majority of those objects are going to pass right through, but if they're not, Jupiter's probably going to be the one to capture it, unless it gets burned up in the sun. You can see that the near-Earth asteroid population is kind of sparse in here. And we've got one more YouTube video, and this is why we care about asteroids. Let me turn this down. So basically just a big shooting star, but it's not very big. Airburst at 33,000 feet, destroyed over 1 million windows, no deaths. If it would have entered 30 seconds later, it would have happened over in New York City. This is in Siberia, Russia. This is the most documented asteroid, inbound asteroid. At this point, it's now not an asteroid, it's a meteor. And you can see right there in the middle, that's where the airburst happens. So why do we care? Anybody want to take a guess at how big that was? School bus. Yeah. School bus. Did that. If it was a little bit larger, it could have come all the way down and done a ground impact. It would have probably done less damage as a ground impact than an airburst. But what we're finding is that these airbursts are actually have a higher risk because of the sonic pressure difference that's going to come through. I mean, it's essentially a nuclear bomb going off at 33,000 feet without the radiation. So what is the current population? We currently know almost 20,000 near-Earth asteroids. This is updated as of noon today. We've discovered almost 500 this year in the first 3 months. Our discovery rate of these objects is increasing every year due to NASA funding, where we're increasing certain telescopes, working longer hours, begging for less money, as any good research project does. We know about 800,000 main belt asteroids. Remember, asteroids don't emit their own light, so we can only detect them when they reflect sunlight. So smaller asteroids are dimmer, requiring larger telescopes to detect. So the problem is that we are detecting as much as we can without asking for a couple $1 billion to build new telescopes. So we get into a situation here where, as the near-Earth asteroid population is increasing, we are discovering more main belt asteroids. But it's almost by accident now, and I'll explain why here in a little bit. Comets we know of about, we know 4,054, and there's about 15 discovered in 2019. So this is a school bus here, a city block remover. A 1 kilometer asteroid's a global killer. NASA's original mandate is we had to find 90% of these. This has been done. We believe we have found 98% of all near-Earth asteroids larger than 1 kilometer. We believe there's 2 or 3 hiding, but again, it's statistics. So, as we all know, there's statistics and lies, and it's about the same thing. So our projection numbers is that there's only 2 or 3 out here left to be found. And we believe they're very, very dark. So it's almost asphalt. So how much light does asphalt reflect? That's what we're trying to find. The population, NASA has now reduced the mandate to finding 90% of the 100-meter objects. We have about 20 20% of this complete with a projected population of 100,000. So a school bus is about 14 meters, so the city block remover, we know of less than 100. Projected population is 100 million. So you can see that as the numbers increase, the smaller you go, but we have 100 million near-Earth asteroids that could produce airbursts and blow out millions of windows. We are hit by these all the time. Just majority of Earth is water. And so when these impact, if they do survive and hit the water, they don't cause a tsunami or anything like that, it's just another wave. I mean, it's a big wave, but it's not detectable typically. So when we're an astronomer, what do we look for? So when discovering an asteroid is somewhat similar to this. You stare at a star field and you look for something that moves. Why? Because stars don't move relative in the same time frame that something in the solar system will. So although stars do move, it's very, very slow in terms of just an inch a century in this image, versus an asteroid, as you can clearly see. So all of our discovery mechanisms right now is to look as much of the sky as possible, as often as possible, and as much as possible, and more often, and a little bit fainter, and a little bit cheaper, so we don't get budget cuts. There are actually 7 discovery telescopes in the world. Every one of these is funded by NASA. There's 2 in Arizona. There's actually 4 in Hawaii. These 1.8 meters have the largest camera in the world before they're building the one for a new telescope in LSST that's not for asteroid work. But you say, okay, you got 2 half-meter telescopes. These are 20 inches. How are they funded for discovery? Well, they actually search the entire sky 7 times a night, but can't go very faint. Versus when you go larger telescope, you can go fainter, but you have a smaller field of view. And so this is just an issue that happens with optics. So the larger your aperture, the harder it is to get a larger field of view, and we need both. We need basically large fields of view with large aperture telescopes, and that's where the billion-dollar price tag comes. We have one satellite that's in a polar orbit. This was the WISE satellite. It was an infrared telescope. It's been turned into an INEO-WISE survey. The big promotion that, if any of you guys hear the spacecraft called INEOCAM, stands for Near Earth Object Camera. It's currently stuck in phase 1 at NASA. This would go to Earth's L1 and be able to take our population of 20% discovered up to 80% in 5 years. So it's been stuck in phase 1 for about 2 years, and NASA is still trying to work to find the $400 million to pay for it. Turns out it's not a popular mission, because it's not making new discoveries, it's just protecting Earth. So we have a world map. Here are the discovery telescopes in Arizona. Here are the discovery telescopes in Hawaii. This is the 1.8 meter in Hawaii, and this is the 60-inch telescope, the 1.5 meter in Arizona. So follow-up. So I'll explain a little bit more here in a second, but we have to discover them, and then we have to actually build the orbit. And it's 2 completely different processes, and I'm funded under the follow-up side. So we have 4 telescopes here in Ashmore, Illinois, and then we have my 3 telescopes in Chile. So Bob Holmes and I operate 7 out of essentially, 11, 12 follow-up telescopes. The Hawaii telescope and the New Mexico telescope are only part-time. They get about 5 nights a month. Versus the 3 in Arizona and Bob Holmes and I, 7, we operate every night, and we try to take a few nights off during full moon. So you can red is still discovery, green is follow-up. But what you can see is that there's nothing on this side. So we're actually only discovering asteroids every 12 hours. It's not a continuous process. So NASA has funded another 0.5 meter down here and a 0.5 meter in South Africa. South Africa has started to become a big NASA-friendly astronomical asset location. As you can see, my work in Chile is NASA's only Southern Hemisphere asset. And so I produce almost 95% of all observations for asteroids that come out of the Southern Hemisphere. The Hawaii telescopes are able to look down to about here, but then I cover everything else. So if you ever get to go out to Bob Holmes, you'll see his famous 4 pole barn setup. Each has a roof that rolls off, and this big one has his 1.3 meter, and this is it sticking out. In Chile, I actually operate that dome, and that dome right now, they have the 0.6 meters, and that's one of the telescopes sticking out around the background. So if you're standing up here, looking down, you can kind of see this beautiful skyline with the telescopes I operate down there, and I've showed this picture before. That's my personal baby, the 1 meter. So I leave tomorrow to actually go do a big maintenance trip on it. All right, so no good presentation is not good without a scientific plot. That is nonsense if you don't know what it's meaning. So colors here, 21st magnitude. To get a green color, it's 2.5 times more difficult than the 21st, and a blue color is 2.5 times more difficult than green, okay? The CSS and the F51, these are the two discoveries, and you can see that they're making majority of the red observations. So that's the easy stuff, but they're not, they're trying to go the entire sky. Versus the rest of us, here are the 4 primary follow-up, and this is Chile and this is Bob Holmes. You can see we don't do as much red, but now we're dominating the green, and only Tholen in Hawaii is doing more of the 23rd magnitude stuff. To put this in perspective, if it's difficult, we do it. If it's not difficult, we don't do it because somebody else will. So there's a whole bunch of people that if you go brighter than 21st, go to 20th magnitude, there's a whole amateur community that can do that, and we basically, it's like easy pickings. It's like taking candy from a kid. Like, go do it, and even if you mess it up, we don't really care because if it gets fainter, then we'll fix it for you. But like one of the asteroids we're going to talk about later that was discovered last month, we're actually the only asset in the world that can get it, and we got one shot in about 5 days. Okay, so asteroids' orbits. We have Keplers Laws. So if you're a physics professor, you'll be very happy that I said Keplers Laws. The reality is all of this is put into a very fancy, very expensive, very classified computer program at NASA. The reason it's classified is they have to remove satellites. And of course, satellites are classified by nature. Okay? So although I've seen some of the code, you can't see all of it. But the system works like this. Here is actually what I produced to NASA. It is strings, maximum characters of 80 long, with all of the data that they need, and it's a data point recording. So the object I think it is, there's a very accurate time, so 2018, April 19th, and there's the rest of the day. Right ascension, which is essentially longitude, where I'm detecting it at this time, declination, which is latitude. How faint I think it is, and 807 is then tells me where on Earth I observed it from. Here's the benefit. When I submit 3 tracklets, okay, time, 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 position, 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 what do we get? Speed and direction, okay? That's all we need. Because the problem with astronomy is we don't have depth perception. We're only taking 2-dimensional images. So how does NASA solve this? We don't know where it is between Earth and Jupiter, so we just assume everything and then rule out bad solutions. So when an asteroid is discovered, this is the kind of plots we deal with. We know along this line, they're assuming 1,000 different orbits. And then they take that information to build uncertainty maps and just where to search in the sky to be able to cover where we think that is. That's where then we come in. The discoveries after telescopes after they discover it don't care about it anymore. It's now my job to continue observing it night after night after night to start ruling out bad orbits, because if the observations don't fit that orbit, then it's not the correct orbit. Think about it this way. Who's a NASCAR fan? All right, not as much as I was hoping. So let me tell you this. Bristol is a very tiny racetrack. It's like a 1/4 mile all the way around. Talladega and like Indianapolis 500, or Brickyard, whatever they call that, is a huge map, okay? So when we get this initial data, all we can basically say is, we know where a race car is right now, but we don't know what size the racetrack is. But Kepler's laws limits and tells us that the race car can't turn around, it has to keep turning left. So if I come back the next day and now I get a data point and I say, okay, you were here today or yesterday and now you're here, then I can rule out, no, you're not at Bristol, because if you were at Bristol, you would have had to have been coming around real fast. Versus if Talladega, no, I would expect you to keep going straight. So you're probably somewhere in between. And we do that the next day and the next day, and you literally just start excluding answers until you're only left with the correct answer. And there's a self-check in here. If I observe and I mess up my observations and we come back tomorrow and observe it, we can now check how accurately have we been able to track this and be able to detect if we have basically made a mistake ourselves and basically reject it and kind of fit a better orbit. There's a lot more mistakes than anybody will admit, including thinking certain asteroids exist when they don't. But that's for a different discussion. So like I said, we assume every possible orbit. After 7 days, we get down to something like this. So after about 5 to 7 days, we can now either exclude or include that it's in a near-Earth asteroid orbit. If it is not in a near-Earth asteroid orbit, we stop caring about it because we can't track all 800,000. We're only worried about this 20,000 population that's growing. After about 30 days, then this object gets to about that. So here's the fun one. 2019 DS1, you can Google it. You probably won't find very much. It was found on February 28th. Closest point to Earth is 0.3 LD. So what is LD? Lunar distance. So was this inside of the lunar orbit? Yes. The size, we put an H magnitude, which is, we don't actually know the size. Let's just put it right there. Unless we do some very fancy calculations and start using infrared telescopes, we're just assuming a size based off of how reflective it is. We say, oh, it could be 5% reflective, and if that case it's larger than what it's reflecting, or if it's really reflective, it's smaller than what we think it is. So if it's not reflective, it's 37 meters. If it's highly reflective, it's 12 meters. So we just, all we can say about this object is it's somewhere between 1 and 3 school buses. But is it a global killer? No, because it's not bigger than a kilometer. Is it a city remover? No, because it's smaller than 100. But it'll take a city block and do an airburst that will cause somebody to have a really bad day. And it's very close to Earth. So why do we care about it? We care about it because what if something alters its orbit? So we have to keep tracking. What if its orbit takes it just right, Jupiter tugs on it for the next 20 years, and all of a sudden now this 0.3 lunar distance drops to say 0.1, or 1/10 of a lunar distance. Now we start having issues with like geosatellites, missions to Mars, missions to the moon, etc. And here's the orbit diagram. So I'm zoomed really far in here, and I want to go over this before I pull up JPL's real orbit diagram. This is real, it's just a screenshot. Mars, Earth is blue, Venus is purple, Mercury is, I don't know, maroon, whatever that color is. What you can actually see here is you'll see white when it is above Earth's orbit. It goes gray when it's below Earth's orbit. And these vertical lines are actually an indication, just to help your eye, of how much higher or lower that object is. Because it's no longer a two-dimensional problem. It's a three-dimensional. Where's Earth?
Right by it.
Yeah, it's actually underneath it. Because at this scale, they're on top of each other. This is when we discovered it at the moment of discovery. It had already passed Earth inside of this is the lunar's orbit. And we discovered it when it was basically heading up. We knew nothing about this. And then we found it as it was leaving. That's the scary part. Because we have to find these before, not after. Because after hurts a little bit more than before. Because mainly I can't go take out $1 million loan and know I'm not going to pay it back, right? So I want to show this real quick because I used to not show this, but I have got a lot of positive feedback, especially from students. This is JPL's website. This is free to anybody. You can type in any asteroid, and it will give you a full program of the movements. Even, all right, you want to move it? Let's go 1 day. You can step it forward and even play. So Earth doing one rotation is a year. So you can go to any time in the future or present, within a couple hundred years is how accurate we have this information, and just watch it go around and around and around until you're bored. Now here's the problem. There's a big lie in here. Anybody know what the lie is? How accurate do we know this orbit? We talked about the idea that in a three-dimensional problem, that we only can see it from discovery to when it gets so faint. And after that, we don't know its orbit. So the uncertainty starts growing. It's almost in a cone shaped around here, starts growing. We know the object will never be here, but there's an error both in the time and the size of what, we call it a large orbit because it's just somewhere in there. This object will go past our current capabilities in 10 days to ever observe it again. The only telescope we have to actually pick this final observation up is the 1 meter in Chile, because of where it's actually going to be. And at that point, it will not be visible from Earth for another 33 years, because its period is 1.03 years. So all of the data we'll ever have on this in the next 33 years has to happen now, and then there's a close approach in 33 years. So that's essential. Now, if we didn't discover it, we would know nothing about it. We only know of 20% of this, there's 100 million of these, and we know of 100. So how many of these are flying by that we have no clue about? We're doing our best, but it's a pretty large sky. So if you're not terrified now, you can show this to your students and then share it and make them just as terrified. And then remind Congress to keep funding my work. There's a theme you should pick up. So the number one question, I got a couple slides left. The number one question I get is, will you call me when we find one? So you're not the only country who has had this same concern. So the UN has created what's called IWAN, the International Asteroid Warning Network. It's a UN resolution. It's got some long resolution number that I don't ever remember. And it basically mandates that all countries who sign into IWAN have to be notified within so many hours after we discover an asteroid that we know is going to impact. So the protocol actually is discovery. At discovery, we run simulations for how practical it is to hit Earth. We try to get follow-up to reduce that. But if the probability is so high, there's an automatic message that's sent to the NASA director, that's sent to the president. The president already has a prepared speech. I saw it. Like not his speech, but like the format of the speech, and they just say insert here kind of deal. And within 20 minutes, the international community has to be notified after the president is. The idea is it gives the president 20 minutes to make his speech. Even if he doesn't, the international alert still goes out. The problem with this, and what we see in the news all the time, asteroid close flyby. I tell all of my family who calls me, says, why didn't you tell me about this asteroid? I say, it's a slow news day. Which one are they talking about today? Because there's literally hundreds at any time making a close flyby. So if there ever is one that we really care about, I won't know maybe more than 5 minutes before you do. And that's just from the automated alert messages that I get that tell me to wake up and go back to work, But you can go onto the IWAN network, you can see what countries have signed on, you can see the alert process as it happens. But when we're discovering hundreds a night and then rejecting these because we don't know how well their orbit is, there's a lot of false alarms. At any one point, we have about 100 to 200 what we call virtual impactors at any point. Now, if you come back 30 days, and that 100 population may be down to 3. And that's just because there hasn't been enough follow-up yet. So discovery's great. We got to get the follow-up operating. And then we can typically reject out the bad orbits. And the bad orbits are collision orbits, just as well as non-collision orbits. Does that kind of make sense? All right, here's the last case. What did Armageddon, the movie, do? Anybody remember?
They project, or they change the orbit.
They drilled. They drilled, put a nuke, blew it up, changed its orbit. Okay? Now, I wanted to add a piece into this presentation that actually tells you, it's actually a copy of that movie, of when the astronomer is reading the coordinates off to NASA headquarters, and he has a wonderful speech in there about being able to name it after his wife, that's somewhat vulgar. It's one of my favorite parts of the movie. But no, there's no red phone. We put red phones in our office to freak people out when they come to visit. There's no phone to NASA. It's email. It's sending this data report. I don't know what kind of orbit. I see hundreds of these a night. I have no clue what orbit each one of it is. I'm targeting a telescope in the most efficient way, getting the data as quickly as I can and sending it into NASA. They have the supercomputers that are running it. They just send me back, say, hey, you're an idiot, you made a mistake, redo your data, or, hey, go get more of this. It's almost automated at this point. So the answer in all of this is, A, there's no red phone to call. Drilling is not good, because when you drill and blow up, you go from one object you have to deal with to millions. So what is the answer? We got 5 minutes. Move it. How far do you have to move?
How far your teleporter will do.
Yeah.
Well, don't move the wrong direction. That's first restriction. So Earth moves in the orbit of Earth in 1 year. Okay? Well, how big is Earth compared to that circumference? So the diameter of Earth compared to the circumference of the orbit?
0.
8 minutes. Earth moves the diameter of Earth in 8 minutes. So how do you go from a direct impact to close approach?
You move it within...
Well, you want some air of uncertainty, so 15 minutes.
Okay.
Okay. But yeah, you only have to speed the asteroid up or slow it down by 8 minutes. That's the only thing mankind has to do is somehow move a 1 kilometer object or smaller or larger 8 minutes. NASA has a mission that they are testing this theory out next year that will launch. It's going to go to a binary asteroid, which where you have a primary asteroid, and you have basically a satellite, almost like a moon orbiting it. And when the spacecraft gets there, it breaks into 2, separates. One has the cameras, one has a big impactor. Breaks off, and it's going to go plunk the, what we call the child asteroid, the moon asteroid. And we're going to see what happens. Now, that orbit of that primary asteroid is in no hazard. This is just an exercise to see if we can even move something. But the ways to do it is you have to go there, land on it, and gently fire a booster to get something to move. Or, as the case that I see all the time, you do not go in front, launch a nuke, and then move it. Okay, that doesn't work. So the reason we need time is if you move that asteroid 1 centimeter today, you'll get the 8 minutes in a decade, is typically this case. So we need to find these asteroids that are on potential collision course 10 to 20 years in advance to then be able to plan the mission, execute the mission, move it 1 centimeter today, to then change the 8 minutes a decade later. Now, if the time frame is shorter, you need more rockets. And let me remind you, we do not even have a rocket that can get a human to Mars yet. Okay? Elon Musk's idea of sending people to Mars is one way. The reason it's one way is there's not enough fuel to get them back. So when you start looking at NASA's new projection for their rocket system, so going back to the moon and going back to Mars, you start seeing ideas of connecting fuel pods, connecting components. This is the only way to make round-trip missions. When we send a spacecraft to Mars, you can never bring it back. We get it close, and then we burn the last little bit of fuel to put it in orbit before we send the rover down. So you have to have some type of rocketry system where you can build massive fuel-required systems to then, in low Earth orbit, to then go to the asteroid and be able to spend literally billions, expel billions of gallons of rocket fuel to move something 1 centimeter. So yeah, so I mean, that's why we need engineering and physics, and sometimes you just gotta kiss and say goodbye. So, all right, here's the final slide. Questions? Yes, sir.
Once an asteroid enters the Earth's atmosphere, how long does it take to come down?
So this is the most difficult question to answer, because it is all about timing. It's a timing problem. Because as the Earth is moving, if you're just a few seconds later, you're going to start grazing the atmosphere, and it could send you all the way around in basically how the space shuttle came in. You're just slowly decreasing speed before versus a direct hit. The answer is about 20 seconds to it can actually be up to an hour. The atmosphere is great at direct impacts because you have the largest pressure change the fastest, and that's how we see these airbursts when they're coming in real hot. But the ones that hit the ground literally graze the atmosphere and slowly start to bleed off energy, bleed off velocity, and they may go around once or twice, losing a little bit of energy before they come in, and those are the ones that successfully make it to the ground. But when they lose more energy, that's good, because lose more velocity, they're losing more energy, they're not going to make that large impact. But when you go from like 14 kilometers a second to 8 kilometers a second, it doesn't actually change the math very well in our favor. It's still going to hurt. Yes, sir.
So 100-meter city killer, right? I mean, I'm just trying to figure out what is the actual range of sizes that nuking it actually is a bad idea. I mean, is there a range where it would be a good idea? I mean, if it's small enough, you do the Bruce Willis thing or whatever and put the nuke in there, and the pieces are smaller, and also it puts them into separate orbits. It gives them also a velocity, so the vast majority of them would actually miss the Earth, and the smaller ones, well, they're smaller.
So it all comes back down to timing. Mm-hmm. When you launch a nuke, you're putting a direct, you have a blast at 1 second. Can you guarantee that the asteroid will be in the correct location to get the maximum force of that blast? Mm-hmm. Versus if you send a spacecraft that you're going to launch, basically land on and then fire a rocket, if you miss, you can come back. If you go into orbit around the asteroid, you're actually semi-stable before then you can. Right.
I mean, but it might be sort of random, you just sort of you drill into it, put the nuke in there, blow it off, you get a bunch of pieces, and...
I mean, if you're talking about 10 meters,
yeah,
nobody's launching a nuke. Nobody's launching a mission. We're on just, wherever it hits, it's going to hit.
Right.
When you get to about 100 meters, again, the risk assessment, how far, if we truly know about this 50 years in advance, we're able to plan for it, we can do something. But if we realize, and our calculations are saying in 48 hours it's going to hit New York, is that even enough time to launch to put a nuke? Because nothing's on standby.
Right.
So there's this very awkward problem of what we could do versus the readiness of the system, and who's going to pay a couple $1 billion a year just to have a rocket constantly fueled on some pad, ready to launch at a moment's notice to go move an asteroid. Yes, ma'am.
You showed the map where the various telescopes are located for discovery and follow-up.
Mm-hmm.
What meshing do we have, say, with European Union telescopes and Japanese and Chinese?
So ESA, which is the European Space Agency, which if you don't know is basically the NASA equivalent, a whole bunch of European countries have gone together to basically make their own space agency. There's a wonderful partnership with them. The problem is that none of their telescopes are full-time on asteroids. So when we find one of these and we need help, they will immediately shut down, and every astronomer wants to be the hero, because we're not. We just sit in front of a computer screen all the time. So anytime we do an exercise with NASA, or we think we actually need additional telescope time, they will drop immediately and point their telescope and get all the data that we want. But they don't have any full-time assets. They're working on it, but again, it's something you can't, you go to build a telescope and it's a 5 to 10 year process. So I expect in the next 5 to 10 years there to be more assets over there. but it's very difficult right now. And remember, the U.S. does not have a good working scientific relationship with China. I am forbidden from speaking to any Chinese national that is not at a U.S. institution. We get emails from them all the time for partnerships, and we are forbidden from talking with them. It's kind of silly, but I want to get paid, so I follow the rules. So China does a lot of work. At no point do I want to say that NASA is better than the Chinese Space Agency, but Chinese Space Agency isn't putting the resources in the asteroid network that NASA is.
So what other countries are, or come close to it at all?
So NASA's willing to spend the money, but we just have to, the reason why you see the plot with everything in the north, it's in U.S. territories. NASA cannot spend money, taxpayer money, outside of the U.S. without congressional approval. The Chile is a loophole because the ground that those telescopes are on is co-owned by both countries. So they created a partnership with Chile, and there's 100,000 acres in there that's actually U.S. territory. So when we go on there, we have to go through security, and it's fake customs, it really is. I mean, it's a security guard going, yeah, but it's technically you're entering U.S. territory. And so that's the loophole to spend money down there. Australia at Siding Spring Observatory, they're a big partner. They've got a relationship, it's a little bit different than what they have with Chile. And South Africa is really the big one. But if you look at the map, so it's more of a global, when we look at these global issues, Southern Hemisphere, you only have 3 choices. Australia, which there's one observatory over here and another big one over there, but that's it. Australia is also at sea level. It doesn't have a big mountain range that you can put telescopes up to get above the atmosphere. South Africa is not that tall, but they are building up, and they're giving the U.S. assets more and more protection because, like the relationship we have in Chile is every telescope in Chile, the Chilean astronomers get 10% on as a flat rate. So Chile has a huge astronomy program, and they don't have to pay $1 for it in their universities. So South Africa is starting to do that, and so South African government is putting more and more protection to make sure that these sites are safe for U.S. astronomers. Now, I'm not saying South Africa is not safe, but in general, when you're walking in, and I'm walking through customs with a $500,000 camera, you need somebody there to stand there and say, yeah, don't question it, here's the paperwork, and move on. I carry this kind of stuff in luggage all the time, because it's cheaper than shipping it at UPS and DHL. But there's also certain protections that when we're going through the airport, there's a security guard standing there. So South Africa is growing more and more, but that's our only 3 choices really for the Southern Hemisphere. It's too hot, typically in Africa. Chinese and Japanese are a good asset, but Europe is so light polluted, there's not good spots.
But what I was thinking of, the array of telescopes that are in the Canary Islands,
Yep.
is from the EU, do they participate in this?
So, not full time, but absolutely. There's big Canary Island telescopes, but again, they're at sea level. You're not as high as some of the mountain ranges in Chile.
But what I'm thinking, I was there once, and I was just driving, and I was a tourist, and I didn't have anybody tell me what I was looking at.
Yeah.
But they're definitely not at sea level. And I don't know what the altitude they are, but they're above the clouds, as I
Yeah.
say. So, and I don't remember what countries and I did talk to someone up there at an information desk. and I don't recall all the different European countries that were in that, but I really was not clear exactly what are they looking at.
Yeah. Yeah, so a lot of these telescopes, there's actually 5 major observatory sites in Chile. One of them is mainly ESA's, the other two of them are mainly NASA, and the other 2 are split between the 2. But what ends up happening is, remember, NASA is doing this through solicitations. NASA is not saying, I want to build a telescope, I want to own a telescope, I'll pay for all the operation costs. It's not how they're doing the majority of their research. It's you at the university send us a grant and explain how you're going to support this overall goal that we've claimed, and then we'll evaluate it on merit, cost, etc., and then give you a yes or no. As far as I know, there have been no U.S. astronomers putting together asteroid work in the Canary Islands. There's a couple reasons, and not to keep this going on longer, but The 1 meter telescope in Chile, the reason I got access to it is nobody had used it for 5 years and they were getting ready to mothball it. And I said, wait, I can do it for real cheap and keep using it. The 4 meter telescope on the mountaintop, I've submitted 7 proposals to it, been rejected every time. Asteroids are considered the vermin of the sky in astronomy. So there's a pecking order, and I'm pretty low. So, really, it's this weird kind of thing where you have to have a company that's willing to take a risk, submit the grant, write the proposal, and try to make some type of salary off of it. And not a lot of people like asteroid research. It's pretty dull. Nobody wants to stay up all night every night. So.
I have one final
Yes,
question for you. So, you've pretty well articulated how things work, how you process the information, send it on. You referred to the vermin of the sky, setting up all night. But you have to have some particular events, discoveries that really stand out so far in your career. Some high points that, can you share?
I got a new computer. The real sad part is, so I discovered so I don't do any discovery, and there was Pan-STARRS had a cloudy month, so I did discover my first near-Earth asteroid last year. It turned out just to be a run-of-the-mill asteroid, but at least it's the checkbox, I've always said there's, William Herschel discovered Uranus. His sister, Caroline, was the first female astronomer, and this was 1880s, 1890s, and she basically was one of the most popular comet discoverers ever. Up until 20 years ago, she had the record for the most. So I've discovered about 5,000 main belt asteroids. I've got my one near-Earth asteroid, but the comet is still kind of on that checkbox. So I try to work deals with some of the big discovery telescopes that say, hey, I'll do a little bit of work for you, but the next comet you get, can you put my name on it? And it hasn't worked out yet. But the big stuff is like the 1 meter. I mean, that was it took over 6 weeks to write the grant. We waited for a year. They said yes, and it took us 7 days to automate the entire thing, and we did it. One quote we had got from a major company was something like $450,000 to do it, and I did it for $40,000. Now I didn't get any of that $40,000, but I was able to hire 2 other contractors that said, yeah, we know how to do it. And so, I mean, it's fun to put stuff like that, but it's. I haven't had any red phone moments, because you just send it in. All right, any other questions? I love questions.
I'll ask one more, sure.
Yep.
The UN International Asteroid Warning Network, well, why would any country choose not to be on it?
So again, the UN, there's a majority of UN resolutions that are, almost all UN resolutions are voluntary.
Mm-hmm.
So there are not a lot of countries that have said no, but it's also one of those that, if you know the UN is going to make an announcement about it, why do you have to do the paperwork to join?
Yeah.
But yeah, we've done exercises last year. So here's the exercise we're doing right now. All right. Before I tell you this, there is no asteroid that we know of that's on a collision course to Earth. Okay. Please don't put it on Twitter. We do not know of it yet. Okay. What we're doing is, you saw with the 2019 DS1 that it was going to do a quick flyby and we weren't going to see it for 33 years. Well, imagine the scenario where we have an asteroid flying by and we won't see it for 5 more years. But in 5 years it has a high impacted probability. So the exercise we're doing right now is, can we get all of the characterization data, so color, spin rate, density, velocity, everything we need within about a 2-day window. Can we get all of NASA's assets operating at the same time for this one event, and then we're giving it to the computer modelers at NASA for them to do all their impact probabilities 5 years in advance. So that's the exercise we're doing right now with an asteroid that's doing a flyby in late May. Is, can we get everything we can right now to then help project in 5 years from now? That asteroid will not hit us in 5 years. It'll do another close flyby. But they just alter the orbit and, give it to the computer programmers. So NASA started to do more and more of these exercises, and you know they're kind of fun because there's a lot of European collaboration there. Actually, the lady at NASA, when we did the exercise last year in their public release department, got fired because when she did the public release, she forgot to put UN or the ESA logo on it. So yeah, they're very sensitive for international agreements. All right, well, thank you. If you guys have any more questions, I'll be around for a while.